to undertake. So we actually shifted that, that site much farther south. This is just a schematic of that same area where we have these sublacustrine fans being accumulated. This is a strike line, so this is a schematic of a profile that's perpendicular to the previous profile in the offshore areas, and we have a whole series of these fans stacked up. And it turns out that the positioning of those is controlled by deformation in the system. So we have to remember that this is a structurally, tectonically very active system, and in order to extract a climate record from this, from these sediments, we have to position ourselves in the right location in the basin. So we would have loved to have driven this vessel up into Lake Malawi. We can't do that, unfortunately. We had to build our own, and so we used an existing fuel barge to produce, to put together a drilling platform. This is about a, this was a 60-meter vessel. It looked really big when we first started this project, this big platform. No problem, we'll be able to, by the time we put all this stuff on it and put 30 people on board, it was a very, very tight place and an unpleasant spot to spend a few months. And it had its own, we had our own logistical troubles. In fact, there was actually pretty severe famine in Mozambique, a couple hundred kilometers from our project site. There was severe malnutrition in a lot of those populations, and here we showed up with all these scientific toys that we had to move across the country, and the tendency was to actually move the food first. So we were quite delayed in getting the drill rig to the barge to install this thing. We had scientists sitting around for about 3 weeks waiting for the equipment to show up. Finally, the truck showed up with 19 of the 20 shipping containers to build the drilling rig, and the one they didn't bring was the base of the rig. So we had to wait another week. In any event, you know, the stuff had to come from various places. One of the most challenging parts of the project, though, was to try to drill in deep water. Right? We wanted to be in a spot. We knew there were a lot of potential stratigraphic gaps in the record, so we wanted to get into deeper water and drill, but anchoring in 600 meters was quite a challenge. So we brought in a portable dynamic positioning system to install on the vessel to keep running for the 6 weeks of the project to allow us to drill continuously. So just a reminder, this is a big lake. It's an inland sea, 700 meters deep, 550 kilometers long. Our drill sites today are anoxic, so there's nothing living down there other than anaerobic microbes. And we expect, we think that the age of the lake and the rift is on the order of 5 to 8 million years. We ended up drilling 2 sites, total of 7 holes in this system in 2 different localities. And we followed standard practices that have been developed by both the ocean drilling and paleolimnological communities, processing most of the cores at the fantastic facility up in Minneapolis, at the LACOR facility. I'll show you just a couple results from the northern site first, which is our much shallower site. So this was drilled in 360 meters of water, and we just very quickly at the end of the project drilled through 3 relatively shallow holes. But what I've superimposed here is a whole core density log on top of some of the high resolution seismic data. And we just look at some of the images here at the very uppermost part of the record, where we have some pretty high amplitude reflections. We actually have well laminated sediments, and these laminated sediments are in fact varves. Okay, we have the light layers are mostly diatoms, which are laid down during the windy season, which is the most productive season in the lake, and then the darker layers are deposited during the rainy season discharge, detrital material. As we go down the core a little bit, still very organic rich, but homogeneous muds. I should mention that in this whole upper part of the section we have no calcium carbonate observed in the bottom of the system, right? And it's largely because we have slightly reduced pH, and the bottom waters are corrosive to accumulation of carbonates. But once we get down lower in the section, our laminations return here, where we have the reflectivity returning, but all these light layers are in fact layers of calcium carbonate. Okay, so we have a major change in the lake system from top to bottom, and by the time we hit this unit at the very base, we have a carbonate-rich and sandy-rich interval here, and we interpret this to be the essentially a migrating shore face. As lake level rose following a series of severe low stands, these deposits were laid down here. So major changes in the landscape, if you will, of the Rift Valley over this time interval. So our main site that we spent most of our effort on was down in the southern part of the Central Basin, down in this area here, and this is a multi-channel seismic profile illustrating the full thickness of the rift fill in this system. This is the Sin Rift basement. We think perhaps on the order of 5 to 8 million years in age, or at least the sediments right above it. And here's our drill core. It's again a density, a whole core density profile superimposed upon that, and we've been able to date the bottom of the core to about 1.3 million years. So again, this is deep water drilling, almost 600 meters of water. There's nothing alive down at that place now, at that location in the middle of the lake today. So I want to take a closer look at this area where we recovered the core, and superimposed upon here again is density in green, and we also have total organic carbon. And one thing we observe in this system is that wherever we have very high density, we have essentially no organic matter or no organic carbon preserved. And where we have very high TOC values, the density drops dramatically. In fact, as we went down the core, we could almost make a prediction just upon lifting up the sections we were processing, which was which. So that same those same acoustic couplets that we saw 80 kilometers up the lake in the form of those stacked sublacustrine deltas, that same kind of acoustic character is exhibited in this very fine-grained hemipelagic environment that we sampled farther south. So I want to. So again, we have this great variability in very organic-rich, homogeneous, and laminated mud, alternating with carbonate, low TOC mud. So we have sort of two end members at a minimum that we can observe very, very quickly in this record. Some enormous changes in lithology going down section and repeating itself in the history of the system. So one thing that surprised us a little bit was the amount of carbonate-rich material and sand in the core. So this was not simply a thick pile of mud in this very deep part of this gigantic lake. There was a lot of other stuff going on down here. And in fact, we had to stop drilling at about 380 meters because the drill, for those of you guys who've spent time on the drill ship, perhaps you're aware that the drillers actually have relatively few controls, right? They can turn the bit, they can put weight on the bit, and they can pump fluid through the pipe, right? And if you stop being able to do one of those three things, you're going to be in trouble very, very quickly. So we actually hit flowing sand at the base of the section, and the driller was like, I'm getting stuck, what should I do? And we had borrowed a drill string from the IODP for this, and had we gotten stuck, there's no way to, there's no bailout, right? There's no help coming from some other drill ship, right? The only solution would have been to cut the pipe and sort of. Anyhow, so we bailed at about that particular point, but we were surprised at how variable the lithologies were in here. So I want to just show you some of the nitty-gritty of the results of the coring. First, looking just at the upper 80 meters from one of the holes at our deep site. Just a few other remarks about what we found in the cores. There was quite a bit of variability in the organic matter. A lot of pelagic diatoms, but also in some cases we found benthic diatoms. So how do you get benthic diatoms in a site that's 600 meters below below the water surface. But we also found quite a bit of terrigenous organic matter. That was quite surprising. We sort of expected these layers of algal-rich muds, but in fact there was a lot of terrigenous organic matter in there, as well as the more classic aquatic freshwater algae. And also we saw quite a bit of variability in the organic geochemistry of this system, although not so much over the past 60,000 years. I'll expand upon this, and perhaps we can talk about this a little more later. So sorry for the complicated drawing here. Initially, what I just want to point out first is this record of TOC. Now, what I've presented is the series of proxies in a nonlinear depth model on top, and then on the bottom we've transformed this into age, and I'll talk a little bit about the age model production in a little bit. But what we can see in this upper 80 meters, we have pretty consistent or constant numbers for something as basic as total organic carbon, but then it gets really wonky as we go to greater depths in the section. And interestingly, where we start to see great reductions in TOC, we see all of a sudden a tremendous abundance of ostracods, which are probably controlling our calcium signature on our scanning XRF. Right? So most of this calcium record is probably controlled by ostracods. And interesting, this is work that was produced by my colleague Andy Cohen. It turns out that the ostracods we found in this core at this deep site don't look like modern Lake Malawi ostracods, right, freshwater systems. In fact, the ostracods we observe bear much greater resemblance to ostracods from places like Lake Turkana, which is a mildly saline and alkaline lake, suggesting that we had very, very different environment back on the order of 75, 100,000 years before present. So we did a couple things with this initial uppermost section here. We were able to constrain this section age-wise much more easily than the deeper record, and we were able to tie back our events that we observe in the core to that seismic grid and actually constrain levels of the lake not only by records from the core but also from the sequence stratigraphy, and propose a lake level section where we see changes on the order of maximum changes of more than 400 meters in water level in this system. So long story short, we have this interval prior to 60,000 years ago of tremendous hydroclimate variability, huge changes in the volume of water in this basin. And then after about 60,000 years ago, Lake Malawi, in contrast to many systems in northern Africa, Lake Malawi stayed pretty wet in comparison. Okay? One thing that surprised us is we didn't observe any major deflection or change in lake level or hydroclimate during at 20,000 years ago, at the time of the last glacial. Right? And in North Africa, this is a huge event. Right? A lot of Lake Victoria went completely dry at 20,000 years ago. That huge expanse of lake was simply a savanna. But that's not a response that we're seeing in Lake Malawi. Now, Lake Malawi this drill site is at about 10 degrees south latitude. So we're quite a ways south of the equator here, even though we're definitely in a tropical environment. So what we proposed for this variability is the fact that we've gone from very much an interval where we have very high orbital eccentricity, perhaps influence of some precession, to a situation where we have much greater hydroclimate stability since about 60,000 years ago. So I'll expand upon this just a little bit in just a second. So our end-member models for the landscape, if you will, are today and since about 60,000 years ago, Lake Malawi has been deep and it's been a freshwater system. The catchment is dominated by savanna and woodland for the most part. We have water column anoxia, stratification in the basin. The coastline is dominated by rocky habitat, actually really important if you're one of those cichlid fish. Okay? And we also have a situation where there's no carbonates accumulating in the deep water. But over several intervals, and maybe even cyclically, prior to 60,000 years ago, we had a vastly different climate. Clearly we had desert in the catchment. We had a situation, we first see an increase in charcoal, for instance, in the cores, and then the charcoal disappears because there's not enough vegetation on the landscape to support wildfire. And the water column during this time, lake level is much lower, and the water column is saline and it's alkaline during this interval. And of course, the habitat's completely altered. So if you're a cichlid, you have to figure something out in a hurry because you mostly have mud and sand flats around. And there's tremendous amount of calcium carbonate accumulating in the system. So these are kind of the end member environments that this system experienced over this 150,000 year interval. Just to recap, this is bathymetry in Lake Malawi today, and if we kind of assume that sedimentation rate and subsidence rates have been in balance over that time interval at least, we postulate that 60,000 years ago the lake was 200 meters lower, 75,000 years ago lower still, and we had perhaps two lakes at a time 100,000 years before present, further enhancing speciation events possibly because of the physical separation of different species flocks. So we had a greatly reduced water volume in the system. And our working model for this is, again, that over this time period where we had very high eccentricity, this may have been due to highly eccentric Earth orbit and enhanced variability. And at least in Lake Malawi or southeastern Africa, we think that the hydroclimate was remarkably stable compared to what was happening in the northern hemisphere East African system at that time. So this actually has implications for our own species. Bringing this back a little bit, we have around 200,000 to 150,000 years ago the first fossil evidence for early modern humans, and the first mitochondrial evidence for early modern humans as well during this time. A number of things happen, though, as we lose this variability in the system. Our species went through this remarkable evolutionary keyhole on the order of 60 to 80,000 years ago. Geneticists have postulated that we went from several million individuals during this time to perhaps just a few thousand individuals and then ramped up considerably after that. This is also the time of the final African exodus when all descendants, all modern humans are descended from a very small group that exited the African continent, or at least all non-Africans are descended from a very small group that exited the African continent at that time. So this is an interesting time for our own evolutionary history. So let me just say a few things about the longer record that has just recently emerged into the has just recently been published, and we're now seeing a number of other follow-on papers coming out. Besides actually collecting getting money for and collecting the core, one of the most challenging parts of this study was to actually date these lake sediments. Right? We can't just use a oxygen isotope stratigraphy. There's no biostratigraphy that we can rely upon. We need absolute ages or paleomagnetic ages. And the youngest part of our core, we used both radiocarbon, and we're also able to identify, colleagues were able to identify the most westward extent of the Toba ash. So this was a cryptotephra found in the Lake Malawi core. Shards, microscopic shards of the eruption from Sumatra at 75,000 years ago were conclusively identified, and that turned out to be a very useful age marker for us. But we have a huge gap, really, in absolute ages between the Toba ash and deeper in the core. We were able to recover just a couple of tephras from this core that were actually datable. Okay, it turned out to be, that was one of the things that actually surprised us considerably, that the whole system wasn't just completely flush with thick tephrins. There were a lot of them, but they were generally very, very small, yielding relatively few phenocrysts, and only 2 were able to be fully dated. We were able to use paleomagnetic reversals in the deeper part of the core, but there has been and continues to be an ongoing discussion and debate amongst the project collaborators about the ages of this one interval between roughly 100 meters or 50 meters and 200 meters depth in the core. So our most recent publication was to establish the most parsimonious age model possible, and paleomag experts are further refining this interval in this particular section. So I just want to say a few things about how we've extracted or promoted this lake level history down through the full 1.3 million year record. And this is largely the work of Bob Lyons' final dissertation chapter. We first essentially tried to quantify lithology, right, using many of the standard measurements that we take in these cores. So we have core imagery, and we extracted information from that. We used TOC and XRF data, as well as physical properties data, to produce a principal components analysis. So essentially a single curve which allowed us to roughly approximate what we think is a history of lake level in the system. And then we took our seismic grid, where we actually had known low lake stages, and calibrated and normalized this record to those specific low stand points. Okay, so this is our first approximation then of lake level PC1. So long story short, we have this principal components record up here representing lake level, and we see changes in lake level that vary from over the full length as much as 500 meters below modern lake level. This is that mega drought interval that I described earlier, but also extending much earlier through the record. So in summary, some of the key observations that we observed, so these are key components that went into the principal components analysis, and then this is just a reference insolation record from this particular latitude. Prior to about 800,000 years ago, the mid-Pleistocene transition, we observed very high frequency changes, although on average the proxies suggest, especially calcium, as well as some of the other indicators, suggest that overall it was a much lower lake and a drier climate on average. Since that time, on average, it's been somewhat wetter, but we've been observing these very pronounced changes in hydroclimate in that system. Okay, so high frequency changes here, but somewhat drier, and then overall wetter conditions since about 800,000 years ago, as expressed in these proxies. So what are the implications for some of these remarkable endemic organisms in this system? We further evaluated the changes in shorelines in the system by going back to the geophysical data set. So we're able to characterize or quantify the nature of the modern shoreline, and we're able to quantify the nature of the ancient shorelines by looking at the character of the size